All right, so we started on last Thursday. We did addition and subtraction of vectors, and we talked about what a vector was and how to find it. We did not talk at all about multiplication, and there is no division. So we're going to talk about the multiplication tonight. There's two different types of multiplication. One is known as the dot product, and one's known as the cross product. They both give us different pieces of information. And the dot product actually is known as a scalar multiple because it actually is just going to give me a scalar product because it's going to give me a specific number, where the cross product actually gives me a vector. So we're going to look at each method, and we're going to see how it actually is used and why we have these. Because when we did the addition and subtraction, it was kind of obvious. It was like we were taking two vectors, we're putting them together to figure out where they ended up basically being as a unit vector. When you're multiplying with the dot product and the cross product, they give us different pieces of information, and how we use them will be a little bit different. So this is the definition of a dot product. So if we're doing the dot product of A and B, it's the A1 times B1 plus A2 times B2 plus A3 times B3. So we're basically going to multiply each of the terms and then add those terms together. That's what a dot product does. There are some properties, as you can see here. So the dot product of A times or A and A is the length of A squared. They are commutative, so you can reverse them. So the dot product of A and B is the same as the dot product of B and A. With the dot product, you can basically do a distribution type process. So you can do the dot product of A and B plus C is the same thing as the dot product of A and B plus the dot product of A and C. If you have a constant term, you can pull that out and actually just multiply it at the end, or you can put it on either one of them. And the dot product of zero, a zero vector and a vector is always zero. Because, and if you think about it, totally makes sense. Every term is zero except for, so it's 0 plus 0 plus 0 in that case. All right, so before we actually get into how it's used, why it's used and stuff like that, let's actually just do a couple really simple ones just to get an idea of how to find it. So we're going to look at these. So it's the first one is the dot product of 2, 4 and 3, negative 1. So it's 2 times 3 plus 4 times negative 1. So I've got 6 plus negative 4, which ends up equaling 2. The next one, we got negative 1 times 6 plus 7 times 2 plus 4 times negative 1/2. So we got negative 6 plus 14 is 8. Minus 2 is 6. And remember, the I, J, and K setup of it is in essence the exact same thing as the numbers. It's just we have the I, J, and the K there, and it's plus or minus. So in this case, the first one is going to be 1 times 0 because there's no I in the second one. Next one is going to be 2 times 2. And then I have negative 3 times negative 1. So 4 minus 4. This one ends up being, wait. Oh, that's plus 4. Oh, plus 3. God, I'm doing addition and screwing up my multiplication. So that's 7, not 0. Negative 3 times negative 1 is not 4. So finding the dot product is pretty straightforward and simple. It's basically just multiplication and add them all together. So that is my actual dot products.
Can there ever be more than just 3 terms?
No, because we don't have fourth dimensional vectors. So it'll either be 2 or 4 or 2 or 3.
Thank you.
No problem. All right. Now let's look at how we can actually use it. So the dot product of A and B actually can allow us to find the angle between those 2 vectors. So the dot product of A and B is equal to the length of vector A times the length of vector B times the cosine of the angle. So we can use this to either find what the dot product is, which we're going to do in the next example, or the one after that, we're going to actually use it to find the angle between the 2 vectors, which is a little more usable case, I should say. So this is one of the situations where we're going to start to be able to use it. So we're going to be able to find that angle between the 2 vectors. So let's do this one first. So we've got our vectors A and B have a length of 4 and 6, and the angle between them is pi over 3. They just want us to find the dot product. So remember, my dot product for this case is the length of A times the length of B times cosine of pi over 3. So my dot product, the length of A is 4. The length of B is 6. Actually, that should have been cosine of theta, but I'll fix it in a second. And then I have cosine of pi over 3. So 4 times 6, and that's 1/2. So my dot product in this case is 12. So not the most useful case of using the dot product. It just allows us to find the dot product given other information about the vectors. The next example that we're going to do is actually going to be the more usable or useful case of the dot product. And that's finding the angle between 2 vectors. All right, so if we modify that equation a little bit, so remember, I have the dot product equals the length of A and times the length of B times the cosine of theta. So if I shift it around a little bit, I got the cosine of theta equals the dot product divided by the length of A and the length of B. So this is where how we can actually use this to figure out what the angle is between 2 vectors, which can be very helpful when we're looking at different physics examples and force and torque and a bunch of other little things that we're going to look at. Well, we're going to look at force in this situation. So the first thing we've got to do for these vectors is find the length. And if you remember, that was just my basically the distance formula. So the length of A is the square root of, so 2 squared plus 2 squared plus -1 squared. So I've got the square root of 9, which is 3. And then the length of B is 5 squared plus 3 squared plus 2 squared, which is the square root of 38. And the next thing I got to find is my dot product. So this will be 2 times 5 plus 2 times -3 plus -1 times 2. 10, -6 is 4, and that ends up being 2. So the dot product is 2. So I've got cosine of theta is 2 over 3 square root of 38. Now, how do we find the angle given that?
We would have to solve for the arc cosine.
Exactly. So we're going to use arc cosine. And it was 2 over 3. 2 divided by 3 square root 38. So the angle ends up being approximately 84 degrees. So 83.8 degrees. All right. So we can now use this one to figure out any angle between two vectors. So we now have a method to be able to figure out the lengths of vectors. We can have a method to figure out which directions some things are, and now we can figure out which the angles they are. One of the pieces that we can use with this is if two vectors are perpendicular, when I'm looking for my dot product, it's going to come out to be 0. So we're going to look at this. And the reason why is if I have cosine of pi over 2, which would mean that the two vectors are perpendicular to each other, cosine of pi over 2 is 0. So that means that my dot product, if I do, it doesn't matter what the length of A and the length of B is. If this part's 0, then the whole thing is 0. So now, based on these two rules that I've had, if I just look at the dot product and find that the dot product comes out to be 0, I know these two vectors are perpendicular, so they meet at the 90 degrees. So it's not very hard to find the dot product of these. So we can easily, quickly find out if the two vectors are perpendicular. So let's
Does orthogonal mean the same thing as perpendicular?
Yeah. Orthogonal. So perpendicular is in is the two-dimensional concept. Orthogonal just means it does it in 3 dimensions. Because technically, so in a two-dimensional plane, I will only have one vector that would be perpendicular to another. However, in a 3-dimensional, you have an infinite number. So that's why they would be considered orthogonal, because there's more than one of them that would actually work. So they want us to show that these two vectors are perpendicular. So we can take them and find my dot product. So I've got 2 times 5 plus 2 times -4 plus -1 times 2. So I've got 10 minus 8 minus 2, which is 0. So since my dot product is 0, they're perpendicular. So it just gives us a quick and easy way to be able to determine if two vectors are going to be perpendicular to each other. The next use case of the dot product is figuring out directional angles or direction cosines. So a direction angles is, so anytime we have a non-zero vector, so that means it's not zero, the direction angles will tell me the angle from each of the axes. So the x-axis, the y-axis, and the z-axis to that actual vector. So we write them in terms of a unit vector. So it's still going to be in that vector space with the cosine of a, the b, and the y. That allows us to find, or gives us another way to represent an actual vector. So we can see here, we have it doesn't make much difference between which ones you're going to use. So the I is just that, the I vector. So remember that's 1, 0, 0. So in essence, if those cancel out, because they're both going to be 1, we have the A1 divided by whatever the length of that vector is. And it's the cosine of that. So the cosine of angle A equals that value there. So we can then use that to find, just like we did with the last problem, or the problem we were finding the angle, we can use the arc cosine to be able to find the actual angles, the directional angles for each of my vectors. So, and the same thing for the second term and the third term in the vector. So if we're looking for the directional angles of this vector here, that vector 1, 2, 3. So the first thing we're going to do is I need to find the length of this. So I've got the square root of 1 squared plus 2 squared plus 3 squared. So that equals the square root of 14. So then I got to look for the cosine of A is going to be 1 over the square root of 14. The cosine of B, because I can't write the, I'm really bad at writing Greek letters. With the B I can, is going to be 2 over the square root of 14. And the cosine of Y, well, it's not Y, is 3 over the square root of 14. So I can now find the arc cosines of each of these. And we can find my directional angles. So we can write this in a couple different ways. So we can actually write this as a vector. So we have, it's the 1 over the square root of 14, the 2 over the square root of 14, and the 3 over the square root of 14. So we can write that as that. Not really useful, but you can. The use case is actually figuring out the components of it, finding the actual lengths or the angles. So my first one is 74.5 degrees. So I've got 74.5, I've got 57.7 degrees, and 36.7 degrees. So if we look at this, so in essence, what this is finding is it's finding these different angles. So the angle from the x-axis, the angle from the y-axis, and the angle from the z-axis. So it's a 74.5 degree angle from the x, a 57.7 degree angle from the y, and a 36.7 degree angle from the z-axis. So again, it's just another use case to be able to find those things. All right, so let's actually do a physics problem. Let's find the work done. So when we're looking at this example, we've got, here, I'll give you the picture of it so you can see that too. So the work done is the length of vector f, the length of vector d times the cosine of theta, which, as we've just shown, is just the dot product of those two vectors. So we can use this to figure out how much work has been done. So in this situation, my work. So I've got the wagon has pulled a distance of 100 meters along a horizontal path. So my distance is 100. My force is 70 newtons. So I've got 70 newtons there. And I'm pulling at an angle of 35 degrees. So it's cosine of 35 degrees. So I have 70 times 100 times the cosine of 35, which comes out to be approximately 5,734 joules of power or of work. In this situation, I had the information, so I didn't really need to use the dot product for it because of the way they gave it to me. In this problem, they're giving it to me in terms of vectors, so I'm going to have to use the dot product to find the information. And both of them will actually give me the same piece of the same information. So I don't necessarily have to have the angles if I have the dot product of it. So it says the force is given by a vector of this. So I've got that vector there, and it moves a particle from point P to Q. So the first thing I have to do in this problem is I need to figure out my displacement vector, my D. So D is the angle from, or the vector from P to Q, which, remember, we can use by just the subtracting the endpoint from the beginning and moving it down to my unit vector. So I've got 4 minus 2, 6 minus 1, and 2 minus 2. So I've got vector 2, 5, and 0. Oh.
Professor, isn't it 2
Yep.
minus 0?
Yes. I was looking at it like, wait, there's not supposed to be a 0 in my answer. That would be why. 2. All right, so I've got my D vector and I've got my F vector. So now to find my work, I'm just going to do the dot product of that. So it is 3 times 2 plus 4 times 5 plus 5 times 2. So 6, 20, 10. So I've got 36 joules of force. So we can do it either way, depending on what information we're given now from it. All right. So that's the dot product. Now we're going to look at the cross product. All right. So this is what the cross product is. So the cross product actually is going to give me a vector. So the dot product gave me a specific value. The cross product is going to give me a vector product. The cross product only works when A and B are 3-dimensional vectors. So you will not see these in 2-dimensional vectors, because what we're looking for with a cross product, one of the things that's we're using it for is to be able to find a vector that is perpendicular to 2 other vectors. So if this was on a plane, 2-dimensional space, then my 2 vectors would have to be parallel to each other for this to work. So, however, in a 3-dimensional plane, I can find a vector that would be perpendicular to any 2 vectors. So that's what we're looking at here. So the vector that we're going to get is one that is perpendicular to both vectors that I'm looking at. So for those of you that remember your matrices, this is the easiest way to set them up. So you've got the definition here, it works. A lot of times it's actually easier just to look at it in terms of the matrix view, because then it's simpler to read. You just have to remember how to actually get it. So remember, when you're looking for the determinant, that's what it was. I'm trying to think of the D word. The determinant of the vector, you're just basically multiplying the cross and subtracting it. So it's A2 times B3 minus A3 times B2. This is set up as a 3x3 determinant, where I, J, and K are put up as the top. So this and this are both basically the exact same thing. It just depends on how you want to write it so that you remember how to do it. Even if it's shown this way, we're going to end up doing it with this. In essence, we're going to do the definition of the vector. It's just a matter of how you're going to be able to write it down to be able to remember what you're going to do with it. So they all mean the same thing.
Are matrices going to come back in calculus?
You do use a little bit of matrices, depending on, and honestly, off the top of my head, I can't think of an example right now. But yes, matrices do come back up. A lot of it ends up doing things like this with the discriminant and stuff, more than actually just doing the full matrix out. You could actually remember when we were doing the, was it section 7.4, when we were doing the partial fractions, You could actually have used matrices to do the system of equations stuff there as well. So I wouldn't totally stress out if you don't remember how to do that, to do matrices. If you're going to use them, the teacher's going to go back over it quickly anyway, because it's not something everybody uses on a regular basis. Except for the discriminant, which does come up quite often. All right, so let's use this. So the cross product of A and B, in this case, is I. 1, 3, 4, 2, 7, -5. So that's set up as the 3-dimension matrice. And then when we break that down, I've got 1, 2, 3, 7, I. And it's minus. So remember this, the signs actually matter in this situation, and they're not all pluses. So, and then we have J, which is 4, 2, -5. Oh, actually, I screwed that up. I wrote the first part and that wasn't. When you're writing whatever letter it is, you eliminate that row. That's how you write this. So -5. That's I minus 1, 2, 4. Okay. And then plus 1, 2, 3, 7. So it's I minus J plus K. So in this case, I've got -15 plus 28 I minus -5 plus 8 J. Where's it minus? Oh, they're all minuses. I'm really having a bad time with my signs today. And then it's 7 minus 6. Okay. So we've got -43I plus 13J plus K. So that is the cross product of A and B.
So with the matrices, you always start with the top left, multiply diagonally, and then subtract that by the top right.
Yep. Diagonally. So yeah, 3 times -5 minus 7 times 4 for the first one. And when you're breaking up the 3 down into the 2, you're, whatever letter you take, so the I, the J, or the K, you eliminate that row or that column, and it's the other 4 numbers. All right. So I said one of the main use cases of the cross product is to find out if, because that cross product is orthogonal to both A and B. So when you look at the cross product, it's going to give you a vector that is perpendicular to both of them. So when we did the dot product, we found out that if the dot product comes out to be 0, then that would be perpendicular. So we can use that to prove this is true. And I haven't done many proofs, but I'm going to do this one. So we've got the cross product of A and B, and then with the dot product of A. So the first thing, let's find, so in essence, we're going to do, this is the, so A2, A3 over B2, B3, and that's times A1 minus A1, A3, B1, B3 times A2 plus A1, B1, A1, A2, B1, B2, and that was all times A3 because I can't write it over there. All right, so if we multiply these out, so I've got A1 times A2 B3 minus A3 B2 minus A2 times A1 B3 minus A3 B1 plus A3 times A1 B2 minus A2 B1. So I've got A1 A2 B3 minus A1 A3 B2 A2 A1 B3 A2 A3 B1 plus A3 A1 B2 minus A3 A2 B1. So if we look at these, I got A1 A2 B3 here, and I've got, what was the other A1? A1 A3 B2 here. No, where's the B3? Oh, there it is. So this one and that one cancels out. Then I've got that one, 1, 3, and that one cancels out. And that one cancels out. So it equals 0. So that just proves using the cross product and the dot product that they would be perpendicular to each other. Now let's actually use this. So a couple things. First one is just like we had with the dot product and cosine, we can find the angle between A and B using sine. So the length of the cross product equals the length of A times the length of B times sine of theta. That also means that if two vectors A and B are parallel, if and only if the cross product is 0. So where we did with the dot product, I can determine if two vectors are perpendicular to each other. The cross product will help me figure out if two vectors are parallel to each other. So because the sine of zero, the angle between them is basically nothing because they're parallel to each other, the cross product would be 0. All right. Let's use oh, there's one. Did I put that over here? Yes, I did. Never mind. I'll do that one in a second. All right. So first thing that we can use this. Says find a vector perpendicular to the plane that passes through these points. So go back to our high school geometry. How many points do I need to make a line?
2,
Correct. How many points do I need to make a plane?
3.
3, as long as they're not linear. So the 3 points kind of have to make a triangle. So, and this is just an extension of what you did in high school geometry when we were looking at it. So now it's 3 dimensions. So we've got the points in 3 dimensions. So we've got the X, Y, and the Z. So we want to find a vector that's perpendicular to this plane. So the first thing I've got to do is find two vectors. So I need a vector and a B vector. So if we look at these 3 points, I can find two vectors with it. So the first one I'm going to find is PQ. So let's find that vector. So that one's going to be -2 minus 1, which would be -3. And then 5 minus 4, which would be 1. And -1 minus 6 would be -7. So that's my first vector. And then I will find vector PR. Now, it doesn't actually matter which two vectors you use. I could have used vector PQ and QR, or QR and PQ. It doesn't make a difference which two vectors you use, because we're looking for a vector that's perpendicular to the plane. So all these vectors are going to be in that same plane. So I've got 1 minus 1, which is 0, -1 minus 4, which is -5, and 1 minus 6, which is -5. So I've got my two vectors. So now I'm going to find my cross product of these. So we've got I, J, K, -3, 1, -7, 0, -5, -5. So 1, -5, -7, -5, pi, minus -3, -7, 0, -5, J, plus -3, 0, 1, -5. Yeah. So I've got -5 minus 35i minus 15 minus negative 7j plus 15. That's 0, not 7. Okay. So I've got negative 40i minus 15j plus 15k. Or negative 40, negative 15. So that's my cross product. So that vector right there is perpendicular to the plane passing through those 3 points. Okay. All right. Now that we can find the cross product is perpendicular, we actually can use a little bit of, well, we can use the information that we had and actually find the area of the parallelogram, of a parallelogram based on this. So the area of a parallelogram, remember, it's base times height. So the length of A, so if you remember, so we had, remember I had the formula was the A cross product of A and B was the length of A. Hold on. Times length of B times sine theta. So if we look at this parallelogram right here, this part right here, that's the height. And that part right there, that's the base. So the cross product of two vectors is going to give me the area of the parallelogram. Now, on two-dimensional space, finding that doesn't really, it's not that difficult to do out without doing vectors. But when we're starting to deal with three-dimensional space, it becomes a little more complicated. So the cross product actually will help us with that. We're going to do the exact same. These are the exact same points I just did in my last problem. So I've got my, remember that's my, that's the perpendicular, that's the cross product, because I've already done that part. So that was the cross product that we got. Rewrite it and get rid of that. So we've got negative 40, negative 15, and 15. So to find the area of, I want the area of a triangle. I'm going to find the area of the parallelogram. and do what to it? How would I find the area of a triangle if I have the parallel? What's the difference between the area of a triangle and area of a parallelogram? It's just cut in half. So all we're going to do is cut my area of my parallelogram in half. So we've got the square root of 40. Square root of 1660. And yes, I'm cheating. Reduces down to 5 square root of 82. And if I want a triangle, we just cut that in half. So that's the area of the triangle. So where these 3 points would be the 3 vertices, 3 of the 4 vertices on the parallelogram. All right. There is some properties of cross products. Notice the first one. The cross product of A and B does not equal the cross product of B times or B and A. It equals the cross product of negative B and A. So they do not come out to be the same. If you multiply one by a constant or a scalar, doesn't matter. You can multiply it by either one or by the cross product at the end. Addition, you can just split that up. So the cross product of A and B plus C is cross product of A and B plus the cross product of A and C. And it doesn't matter if you do the addition or cross product first or second, same process comes out. You can also do the dot product and the cross product interchangeably. So the dot product of A times B, the cross product of B and C, is the same as the cross product of A and B and the dot product of C. If you were doing multiple cross products, this is the dot product of A and C times B minus the dot product of A and B times C. So remember, B and C are vectors. So we'd find this and then find this one and we'd subtract those 2 vectors. So it still would come out to be a vector at the end. The next thing we're going to use, or the other one that we have, is what's known as a triple product. So if you look at B right here, that's what's known as the triple product. So that is when you have or a dot product of a vector and a cross product. When you set this up, and we kind of did this a little bit ago when we were looking at the figuring out if or proving that the cross product is going to be perpendicular to the other vectors, is the first vector is your I, J, and K. So we have those numbers or those letters there. So you no longer have the I, J, and K. That's going to be a vector. So when you do this, you're going to end up getting a single number out because the dot product will always give you a single value.
So the setup for the triple product would still be the same. Instead of I, J, and K, we just put A1 on the outside.
Yep, exactly. Yeah, it's still going to be set up and done the same way. It's just you're not going to have an I, J, and K anymore. You're going to have actual numbers there.
All right, thank you.
We're going to do one of those in a second, actually, so you can see it. All right, let's use this. Let's use the triple product. All right, so I'm going to use the scalar triple product to show that three vectors, or that these three vectors are all coplanar. So if I have three vectors that are coplanar, that means that they are all that. If they're going to be coplanar, when we figure them out, your scalar triple product will come out to be a 0. Now, the reason why. Let me show you that.
Does coplanar just mean that they habitate the same plane of existence?
Yep. Yeah, they're all on the same plane. So let me look. So right here. So if we look at these three vectors, A, C, and B, those three vectors are not coplanar. Okay, because the C goes out. So if I had A, B, and the C was up here as the top, or the C was the one over here, those would be all coplanar, and that's why they come out to be 0, because I have two lines that are parallel to each other. So in essence, it means if I have three vectors that are coplanar, I cannot find a vector. There is no vector that's going to be perpendicular to them all, because they are all on the same plane. That's why it comes out to be 0. Just easier to show you two as a picture. So we've got our A dot and across the B and C. And just as we're looking at, remember this, it doesn't matter which one I do as the cross product and which one I do as the dot, it'll still come out to be the same answer. So it's just easier to write the A dot B cross C. So when I set this up, I have the A, the B, and the C. So this ends up coming out to be, so I've got -1, -9, 4, 18 times 1 minus 2, 4, 0, 18 times 4 plus 2, 1, 0, -9 times -7. So I've got -18 minus -36 times 1. I've got 4 times 36. Then I got -7 times -18. So I got 18 that ends up coming out to be 0. So that means there is no vector that can be parallel or perpendicular to all of them. So that means those 3 vectors must be coplanar. All right, let's do a physics problem. So we're going to look at torque. So torque, actually, T, is really the cross product of our position vector and our force. So and that's the absolute value of torque, T, is the length of that vector, which also, remember, that was the same thing as saying the length of R, the length of F times sine theta. So I can find torque using this equation. So in this situation, I've got a bolt that's being tightened by applying a 40 Newton force. So I know my F. So the length of F is 40. And my R, or the length of my position vector, which is my wrench, is 0.25 meters. And as the picture shows, my angle that I'm pulling at is 75 degrees. So my theta is 75 degrees. So is going to be 40 or 0.25 times 40 times sine of 75 degrees. 0.25 times 40 is 10. And the sine of 75 is 0.966. So this comes out to be 9.66. Newtons meters. So the actual example goes, this is only true if the bolt is right threaded, because we'd be pulling downward. If I was going the other direction, my angle would be different. Because it wouldn't be 75, it would be 105. Because it'd be the angle on this side. And that's it. That's cross product and dot product. So you can, if you want to go further, because we're not in this, but by finding out perpendiculars and finding out parallels, we can actually use these concepts of cross product and dot product to actually find our equations of planes and our equations of lines that are tangent to things, and all that other stuff when we're looking at in 3-dimensional space now. So that's why these functions and these processes are so important. Questions? All right.